Incoming start from Bingo 2. Watches are revealed.
In September 1944, England had no defense against German supersonic missiles. Just 3 months and 2 days after Allied armies landed in France, Germany unleashed the world's first ballistic missiles on London. The V-2 had a top speed of 3,300 miles an hour, making it one of the most significant technology achievements of World War II. British radars of the day could track the missile and compute the time and point of impact. But the V-2 could not be intercepted by any defensive system in the Allied arsenal. Officials calculated that it would take a barrage of 320,000 anti-aircraft shells to destroy a V-2. If this had been done, the duds and particles of those shells would have produced more casualties than an exploding V-2. 11 months later, in August 1945, an American technological breakthrough would end the war. Atomic bombs were dropped on Hiroshima and Nagasaki, leading to Japan's surrender 6 years after hostilities began in Europe. These war years brought many engineering and scientific developments. Today, more than half a century later, few of them remain as relevant as the invention of the ballistic missile and the atomic bomb. Together, they represent the world's ultimate weapons and the ultimate systems to deliver those weapons. The end of the Cold War has greatly reduced the threat of ballistic missiles. But as we saw in the Persian Gulf War in 1991, the threat has not been eliminated. Today, just like England in 1944, we have no defense against a long-range strategic missile fired at the United States from another country. The U.S. Army Space and Missile Defense Command is the world's leader in ballistic missile defense technology. but none of the systems developed over the past 4 decades are currently deployed. Concern over strategic missiles goes back to 1946, when a board chaired by General Joseph Stilwell concluded that guided missiles traveling at extreme altitudes and velocities in excess of supersonic speed are inevitable. This same War Department board recommended that development of defensive measures against atomic weapons be accorded priority over all other national defense projects. The concern, as well as the threat, increased in September 1949 when the Soviet Union exploded an atomic device and experimented with long-range bombers and missiles. In the early 1950s, U.S. anti-aircraft missiles like the Nike Ajax were successfully tested and deployed. Then, in March 1955, the Army Ordnance Corps at Redstone Arsenal, Huntsville, Alabama, contracted with Bell Laboratories for a study called Nike 2 that would provide research focus for the first anti-ballistic missile program. The program took on a new sense of urgency, however, in 1957, when the Soviet Union launched the world's first satellite, Sputnik 1. Redstone Arsenal was selected to demonstrate an ABM capability, and the program was renamed Nike Zeus. The major limiting factor was not the missile, but radar technology. Each Nike Zeus battery required a series of rotating mechanical antennas to isolate incoming re-entry vehicles from debris or decoys. Computing power was also limited until the development of improved computer components by Bell Labs. Despite steady advances in both radar and computers, Secretary of Defense Robert McNamara concluded in January 1962 that it was neither technically feasible nor cost-effective to deploy Nike Zeus. He recommended continued research and development, however, and in December 1962, a Nike Zeus system on Kwajalein Atoll in the Marshall Islands successfully intercepted an incoming ICBM warhead fired from Vandenberg Air Force Base in California, 4,800 miles away. A month later, in January 1963, McNamara directed the Army at Redstone Arsenal to develop a new ABM system, temporarily designated Nike X. By the end of 1963, the Nike X Project Office awarded a contract for an entirely new type of radar to the Sylvania Electronics Systems. Called phased array radar instead of rotating mechanically, the base was stationary while the beam was moved electronically, providing a far greater missile tracking and target discrimination capability. The Nike X team also determined that a computer capable of performing 30 million calculations per second would be required. Ignoring critics, the Army and its Western Electric Bell Labs contractor team proceeded with development of a multiprocessor that delivered this extraordinarily high-speed data processing. The first full-scale model was in operation by 1967. As the program evolved, improvements continued on the long-range Nike X interceptor missile, and it was renamed Spartan. At the same time, a very fast, shorter-range interceptor, the Sprint, was being developed. As with most programs that push the limits of technology, not all the early tests were successful. But once Sprint was perfected, it was so fast that in flight, it became incandescent. With Spartan and Sprint, the United States now had the technology to deploy an ABM system to protect its cities or other vital assets such as military bases. Although Moscow had already deployed its own ABM system, many critics argued that deploying effective interceptors to destroy incoming warheads would destabilize the arms race with the Soviet Union. Just as the President's Science Advisory Committee had recommended in 1960 that fallout shelters have priority over development of Nike Zeus, 7 years later, critics of the ABM program argued that the doctrine of mutual assured destruction, known as MAD, should remain the United States' only defense against a Soviet nuclear missile attack. In June 1967, President Lyndon Johnson and Soviet Premier Alexei Kosygin met in Glassboro, New Jersey. Johnson and Defense Secretary McNamara wanted Kosygin to suspend deployment of an ABM system around Moscow and offered to negotiate restrictions on defensive weapons. Kosygin refused, declaring defense is moral, offense is immoral. 3 months later, McNamara announced the administration's decision to deploy an ABM system, the Sentinel, as a defense against a possible Chinese or nth country attack.
After a detailed review then of all of these considerations, we've decided to go forward with this Chinese-oriented ABM system.
Initial deployment of Sentinel was to consist of 480 Spartans and 192 Sprints at various sites around the country. Work actually began on site preparation in the Boston area, but it was short-lived. Increasing public fears of nuclear missiles deployed in urban areas resulted in the suspension of the Sentinel program. Following a review of the program, President Richard Nixon gave it yet another name and a new mission.
After long study of all of the options available, I have concluded that the Sentinel program, previously adopted, should be substantially modified. The new program that I have recommended this morning to the leaders and that I announced today is one that perhaps best can be described as a safeguard program.
The debate over safeguard raged in Congress throughout the spring and summer of 1969, with the Senate finally approving deployment by one vote in August. As Senator Winston L. Prouty put it, if missiles were incoming, the president would only have one option. I want to give him another button to push.
This is a purely defensive setup. I think it is going to persuade many of the nations that it's better to adopt defensive policies rather than to concentrate on the production of offensive weapons.
As approved, the bill authorized 2 sites near Air Force ICBM bases, near Grand Forks, North Dakota, and Malmstrom, Montana. The first site was to be operational in 54 months. As construction progressed, the United States and the Soviet Union began strategic arms limitation talks, known as SALT. Out of these talks came the Anti-Ballistic Missile Treaty of 1972, which allowed both nations 2 ABM sites, one of which had to be located at the national capital. As a result, work was discontinued on the Montana site, and it was demolished. The Stanley R. Michelson Safeguard Complex became fully operational on September 28, 1975, 3 days ahead of schedule. But on February 10, 1976, Congress terminated the Safeguard ABM mission. The huge perimeter acquisition radar was turned over to the Air Force to become part of the National Early Warning System. But while research has continued on ballistic missile defense systems, including several spectacularly successful tests, the United States has not had an operational anti-ballistic missile system for more than 2 decades. Nothing is constant but change, a Greek philosopher said. But according to a French skeptic, the more things change, the more they stay the same. Chaos, uncertainty, the confusion of combat, the swirl of conflict, the fog of war. Gotta make some sense. Gotta make some order. Gotta know where you are, where the enemy is, where your friends are, if you're gonna survive and fight and win. That's your job as a battlefield commander. Bring control out of chaos, sense out of confusion, decisive victory out of conflict. The purpose and nature of war hasn't changed. But the tools and the tempo have. Vehicles and troops move farther, faster than ever before. Weapons deliver deadly fire on more distant targets, faster and more accurately. The high ground for observing and communicating reaches all the way into space. Today's battlefield is deeper, higher, faster paced, and deadlier than ever before. And the Army Space and Missile Defense Command is responding to the challenges of the 21st century battlefield with the power of space and technology. U.S. Army active forces at the time of Desert Storm totaled about 700,000. Today, as a result of shrinking budgets and downsizing, Army active forces total around 480,000. This means Army combat forces today have to be nearly twice as effective, twice as lethal to their adversaries, and twice as hard for the enemy to destroy. They have to see deep, shoot deep, and maneuver deep, and dominate the battlefield. When the next conflict is likely as not to be in unknown territory, proficiency in information warfare is the key. The right information to the right people at the right time. It starts as soon as the next destination is known, even while they're en route aboard aircraft. Terrain elevation data, added to satellite imagery, produces 3D fly-through views of the likely field of battle. They arrive on site as virtual combat veterans of the area. Army Space Support teams from SMDC's Army Space Command accompany early deploying units to provide them with space products such as intelligence and planning and operational products like worldwide communications by way of the SMDC operated Defense Satellite Communications System and other satellite systems with weather data and other imagery. To win in the information age, U.S. forces have to know more and sooner than the enemy, communicate better than the enemy, decide quicker than the enemy, and execute faster than the enemy. The continuing need remains information, usable information, knowledge. The Army TINCAP systems, developed by SMDC, let the tactical commander see deep and hear deep on the battlefield and assess the impact of shooting deep with time-sensitive intelligence from national assets.
Identification, classification.
Once the fighting starts, Joint Tactical Ground Stations provide the only in-theater tactical ballistic missile attack warning capability on the battlefield.
Operator, we have a valid launch on track 0002, heading 090 degrees.
All these capabilities come together in a Space and Missile Defense Tactical Operations Center, or SMD-TOC,